All right, momentum, something we worked out in class, is through Newton's second and third law. We can relate impulses. So F net delta t must be equal to m delta v. That's through Newton's second law. We call this thing an impulse, which is j. We call this thing change in momentum, which is delta p. So that means that j is a force. We're going to put in average force for ourselves multiplied by a period of time that average force is applied. And p is a mass of an object multiplied by its velocity. These are all vectors because force is a vector and velocity is a vector. So what this means is if you know the impulse applied to an object, then you know the change in momentum of the object. That's very useful. That's from Newton's second law. And from Newton's third law, I push on you, you push on me, we were able to show that in collisions of two objects, then necessarily, if we consider only the internal forces, the forces applied on the colliding objects by each other, that P initial for the system has to be equal to P final for the system, which is useful because if I have two colliding objects, then I can say that M initial 1, V initial 1 plus M initial 2, V initial 2 must be equal to M final 1, V final 1 plus M final 2, V final 2. And for most of your problems, the finals and initials on the mass aren't so consequential because the masses of the things are not changing. Where did this come from? This came from how impulses change momentum, and that the impulse applied on object A by object B is necessarily equal to the impulse applied on object B by object A. And that's because the forces are third law pairs, equal and opposite, and the collision time is necessarily the same experienced by both objects when they collide with each other. So since the impulses are equal and opposite, if I was to get the total momentum of the system, change in momentum of the system, it would always have to be zero because the two will just cancel with each other. And that's how we get to this conservation of momentum. We also talked about specific types of collisions, how you can have perfectly inelastic, all the way to perfectly elastic. And here, VF is same for both objects that collide. That's what makes something perfectly inelastic, and necessarily there will be a change in thermal energy. So that's not equal to zero, which means that you also have a change in kinetic energy. Perfectly elastic, what makes that thing special is that there is no change in kinetic energy. So not only is total energy conserved, the type of energy is conserved. In between is something in between. And then finally, for the case of perfectly elastic collisions, we showed that if you have a type where two objects collide and object one has some non-zero velocity initially, and object two has a zero velocity initially, you can work out the final velocities of both objects. And that's pretty much it for chapter 8.